If everything in the known universe is composed of atoms, then we should all have a basic understanding of the atom and the three fundamental subatomic particles: the proton, the neutron, and the electron. Therefore, the goal of this chapter is to define and deduce the number of protons, neutrons, and electrons that an atom possesses, and understand where these subatomic particles reside within an atom. There is a great deal of information that can be gleaned from the periodic table. In fact, many refer to the periodic table as the world's greatest cheat sheet. For example, what makes helium different from all the other elements found within the periodic table? Examining helium closer, we see that the atomic number for helium is 2. The atomic number indicates how many protons are found in the nucleus of an atom. Thus, elemental identity comes from the number of protons. In other words, for helium to be helium, it must possess only 2 protons. If helium gained a proton, the atomic number would become 3, which means its elemental identity would also change from helium to lithium. The 2 protons of helium exist at the center of the atom called the nucleus, and each proton has a positive charge. The 2 similar positive charges should repel each other, but an attractive force, called a strong nuclear force, helps to overcome this repulsion, and the 2 subatomic particles are actually attracted to each other. It should be noted that this attraction only occurs at the subatomic level. The repulsions are further reduced with the help of neutrons. The neutrons are also found inside the nucleus, which are slightly heavier than the protons and have no charge. It may help to think of a neutron as nuclear glue that increases the extent of the strong nuclear force, which helps hold the protons together. The sum of the protons and neutrons is referred to as the mass number. In this example, helium has 2 protons and 2 neutrons. Thus, the mass number is 4, which is often given in the upper left-hand corner of the element, and the atomic number is 2, which appears in the lower left-hand corner. However, the atomic number is often omitted. After all, atomic number can be deduced from the periodic table if the elemental symbol is given. For example, the atomic number in the lower left-hand corner does not have to be included for carbon if we have access to a periodic table. From the periodic table, we see that carbon has an atomic number of 6. Thus, there are 6 protons present. To deduce the number of neutrons, we simply subtract the number of protons from the mass number. Thus, there are 6 neutrons. Remember, the mass number is the sum of the neutrons and the protons. At this point, we can introduce isotopes. Isotopes are atoms with the same number of protons but different number of neutrons. For example, the 2 common isotopes of carbon are carbon-12 and carbon-13. They both have the same number of protons, 6, but the number of neutrons are different. Carbon-12 has 6, and carbon-13 has 7 neutrons, which were deduced from subtracting the number of protons from the mass number. Now let's look at 2 isotopes of chlorine and deduce their numbers of protons and neutrons. Here again, the atomic number in the lower left-hand corner has been omitted because we have access to a periodic table. Examining the periodic table, we see that chlorine is atomic number 17. Thus, both isotopes have 17 protons. The mass numbers, 35 and 37, then allow us to deduce the number of neutrons for each isotope, 18 and 20. The fractional abundance of the chlorine-35 isotope is 75.53%, and the fractional abundance of the chlorine-37 isotope is 24.47%. Put another way, in any sample of pure chlorine, 75.53% of the sample is the chlorine-35 isotope, and 24.47% is the chlorine-37 isotope. Now let's use this data to introduce the atomic mass of an element. The atomic mass of an element is the weighted average of the masses of the naturally occurring isotopes. But what are the masses of each isotope and how are they calculated? To answer this question, we need to introduce the atomic mass unit, or AMU. A proton's actual weight is a fraction of a gram. Thus, it is easier if we simplify this value to 1 atomic mass unit. Although a neutron is slightly heavier than a proton, we will also simplify this value to 1 AMU. Taking the weighted average of the 2 chlorine isotopes means we have to account for the fractional abundance of both of these isotopes. Thus, the chlorine-35 isotope is the major isotope, and its mass needs to be accounted for approximately 75% of the time, while the mass of the minor isotope, chlorine-37, needs to be accounted for approximately 25% of the time. For simplicity, we have rounded the fractional abundances and masses for both isotopes within our calculations. As we expected, the atomic mass, 35.5 AMU, lies closer to the mass number of the more abundant chlorine-35 isotope. In the previous carbon example, we examined 2 isotopes of carbon. The carbon-12 isotope is the major isotope, and its mass needs to be accounted for 98.89% of the time, while the mass of the minor isotope, carbon-13, needs to be accounted for 1.11% of the time. As we expected, the atomic mass for carbon, 12.01 AMU, lies much closer to the mass number of the more abundant isotope. Thus, the atomic mass of an element depends on both the mass and the relative abundance of each of the element's isotopes. The third subatomic particle, the electron, is a negatively charged particle that resides outside of the nucleus within orbitals. In the next chapter, we will examine orbitals in much more detail, but for now we will simply focus on how to ascertain the number of electrons that an atom possesses and how it affects the charge of the atom. The actual charge that the positively charged proton and negatively charged electron possesses is very small. Thus, for simplicity, we will assign a positive 1 and a negative 1 charge to these subatomic particles. If there are the same number of electrons as protons, all charges will cancel, and the atom will have no charge. However, if a different number of electrons than protons exists within an atom, then the atom will have a charge, called an ion, and this charge is written in the upper right-hand corner. If an atom has more electrons than protons, this ion is called an anion, which has a negative charge, and if an atom has less electrons than protons, this ion is called a cation, which has a positive charge. For example, if carbon gained an extra electron, there would be 1 more electron than protons. Thus, it would have 7 electrons and a negative 1 charge. In the next couple of examples, it may help to think of an anion as an atom that has gained electrons and a cation as an atom that has lost electrons. From the information given, we do not need to consult a periodic table to deduce the number of protons for the fluorine-19 anion. However, if the atomic number of 9 was not given, we could have simply found fluorine on the periodic table and deduced its atomic number. Thus, there are 9 protons. The number of neutrons is calculated from subtracting the number of protons from the mass number, which gives 10 neutrons. The negative 1 charge indicates there is 1 extra electron when compared to the number of protons. Thus, there are 10 electrons. Here, the atomic number of 12 is given for the magnesium-24 cation. Thus, there are 12 protons. Again, the number of neutrons is calculated from subtracting the number of protons from the mass number, which affords 12 neutrons. And finally, the positive 2 charge indicates we have lost 2 electrons when compared to the number of positive charges. Thus, there are 10 electrons. It is always a good idea to check your work. For example, if you deduced there was 12 protons and 10 electrons, you can simply add them together. 12 positives with 10 negatives adds to +2, which matches the charge of this cation. It is important to be able to quickly deduce the quantity of each of these subatomic particles so that you can gain a better understanding of the atom you are examining. In fact, different atoms have distinct chemical properties and reactivities due to the different numbers of protons, neutrons, and electrons. Now that we have developed skills to deduce numbers of protons, neutrons, and electrons for any isotope or ion, let us start to get a feel for the relative sizes of these particles within an atom. We have already learned that the proton is positively charged and the neutron has no charge, that they both reside within the nucleus, are about the same size, and they are both approximately 2,000 times bigger than a negatively charged electron, which resides in an orbital. The term nucleus loosely translates to little nut in Latin. So how small is the nucleus compared with the size of the orbital where the electron resides? Imagine you are standing in the middle of one half of a soccer field, and you are holding a grain of rice in your hand, which represents the size of a proton in this analogy. Now imagine the size of an electron, which is 1/2000th the size of that grain of rice. This very small particle, our electron, moves rapidly and randomly inside this giant sphere with a fixed amount of energy. This giant sphere is called an orbital, which is the whole half of the field above and below you. This is what an atom of hydrogen is like. As you can see, an atom is a whole lot of empty space. Even more mind-boggling is the fact that an atom is so small that a human hair is approximately 1 million carbon atoms in width. In the early 1900s, many brilliant minds were changing the landscape of science. In particular, quantum theory was emerging and changing the way we viewed the atom. One of the great results of quantum mechanics was the orbital, which is where the electrons reside. An orbital should never be confused with an orbit. An orbit is a mathematically defined pathway. For example, how the Earth orbits the Sun. Using classical Newtonian physics, we can predict where the Earth will be on the orbit at some time t and where it was at some time t. In the past, you may have seen a similar simplified model of the atom where the electron is orbiting the nucleus on a mathematically defined pathway, which couldn't be further from the truth. An orbital is a much more complicated concept than an orbit. In fact, we know nothing about how the electron moves around the nucleus. Thus, quantum mechanics demonstrated that electrons did not move around in neat orbits, but existed in regions called orbitals with a fixed amount of energy. In simplest terms, an orbital is a three-dimensional region or shape, and you can expect to find an electron inside this shape 90% of the time. It may help to think of this shape as a boundary surface. The electron is more likely to be inside this boundary shape rather than outside the boundary. Let's apply this concept of boundary shape to the electron of the hydrogen atom, which has one proton in the nucleus and one electron in a surrounding orbital. If you imagine the electron as moving in a random manner with fixed energy around the nucleus, and then imagine that we take a picture of this electron every second for a day, a week, or month, we see that all these pictures laid on top of one another begin to form an electron cloud around the nucleus. Remember, all these hypothetical pictures or data points represent where the electron has been over time. If we now attempt to create a three-dimensional surface to encompass 90% of all these data points, we obtain a sphere, which is often called the boundary surface. The creation of this boundary surface for the hydrogen atom, which is called an s orbital, requires some pretty complex calculus. Thus, if an electron is in an orbital, the electron has a fixed amount of energy, and the orbital is a three-dimensional region around the nucleus that indicates the probable location of that electron 90% of the time. There are many different orbitals for the electrons to reside. The successive solutions or orbitals from quantum mechanics increase in relative energy. When we add the shapes to the energy terms, we get the following electron configuration diagram, which shows all the orbitals available for electrons to reside. The orbitals fall into one of four broad categories: s, p, d, and f orbitals. Interestingly, there is one solution each time an s orbital is obtained, 3 solutions of the same energy each time a p solution is obtained, 5 solutions of the same energy each time a d solution is obtained, and 7 solutions of the same energy each time a F solution is obtained. In the next chapter, we will revisit this diagram in detail to aid in writing electron configurations. For now, let's just focus on what this diagram represents: the orbitals, and each of these lines abstractly represents an orbital. For example, the first line on the electron configuration diagram is the 1s orbital, and it is a sphere. This is where the first 2 electrons of an atom can be found 90% of the time. In addition, all of the s orbitals are shaped like spheres. The 3 2p orbitals are shaped like dumbbells oriented along the 3 axes: the 2px, 2py, and 2pz. For convenience, your instructor will often shrink them down to 1/3 of their size so that they are easier to draw. If we continue to go up in relative energy, the shapes of the orbitals become increasingly more complicated, as demonstrated by the 3D orbital shapes. And it is unlikely that your instructor will hold you accountable for these shapes. Although this diagram may look complicated, remember that each line abstractly represents an orbital, and that all of these orbitals overlap on the same atom. Here you can see that a 1s orbital is the first orbital that the electrons will reside in. Then the 2s orbital is on top of that. Then the 3 2p orbitals are on top of them, and so on, until the necessary amount of orbitals are present to house all of the electrons that an atom may possess. If orbitals are where electrons can be found 90% of the time, in the next chapter we will examine how many electrons are in each orbital and the order in which they are filled by an atom. The arrangement of electrons in an atom is known as the atom's electron configuration. Think of this as finding a home for each electron. Electrons want to be in the lowest energy arrangement called the ground state electron configuration, and to accomplish this we need to follow 3 basic rules. The Aufbau principle tells us the order the orbitals are filled. Aufbau is a German word meaning to build up. Just like building a house, we need to start at the bottom floor. When that is completely finished, we begin on the next floor. Thus, electrons are added to the lowest energy orbital first, and then we work our way up in relative energy. This means that on the electron configuration diagram, electrons are placed into the 1s orbital first, then the 2s, followed by the 2p, 3s, 3p, and so on until the necessary amount of orbitals are filled to house all of the electrons that an atom may possess. The next rule is called the Pauli exclusion principle, which simply translates to only 2 electrons per orbital with opposite spin. Within the electron configuration diagram, we will represent electrons as half arrows. The first arrow is up and the second arrow is down. Remember that each line on this diagram abstractly represents an orbital and that each arrow represents an electron in that orbital. Below the diagram is the electron configuration notation, which utilizes exponents to indicate the number of electrons within each orbital. The third and last rule is called Hünd's rule, which states orbitals of equal energy are occupied by 1 electron before any orbital is occupied by a second electron. Now let's review these 3 basic rules. The first electron goes into lowest energy orbital, 1s orbital, which is the Aufbau rule. The second electron goes into that same orbital with opposite spin. The Pauli exclusion principle states we can only have 2 electrons per orbital, thus the third electron goes into the next highest energy orbital, the 2s. The fourth electron also goes into the 2s orbital, but with opposite spin, followed by the fifth electron filling one of the 2p orbitals. Hünd's rule states that the 6th electron will go into a different 2p orbital because we should fill the orbitals one at a time across an energy level before pairing electrons. Subsequent electrons are added following these 3 basic rules until the required amount of electrons are added. To work this example problem, we first need to consult the periodic table to ascertain how many electrons are in a neutral atom of carbon. In the first chapter, we learned how to quickly deduce the number of electrons, and we will need this skill now. The atomic number of carbon is 6. Thus, a neutral atom of carbon has 6 electrons. Therefore, this problem simply translates to finding a home for 6 electrons. Following our 3 simple rules, we place all 6 electrons into our diagram as shown. Start at the bottom, working our way up, 2 electrons per orbital with opposite spin, and fill the orbitals one at a time across an energy level before pairing electrons. In this example, we have one more electron than the atomic number of fluorine. Thus, examining the periodic table, we see that fluorine's atomic number is 9, which means there are 9 protons and 10 electrons if we have a -1 charge. Thus, the problem is really asking us to find a home for 10 electrons. Again, following our 3 simple rules, we place all 10 electrons into our diagram as shown. In this example, the calcium atom has lost 2 electrons when compared to the number of protons. Thus, examining the periodic table, we see that calcium's atomic number is 20, which means there are 20 protons and 18 electrons if we have a +2 charge. Thus, the problem is really asking us to find a home for 18 electrons. Again, following our 3 simple rules, we place all 18 electrons into our diagram as shown. First, we need to consult the periodic table to ascertain how many electrons are in a neutral atom of gallium, which will be the same as the atomic number for gallium. Gallium's atomic number is 31, which means there are 31 electrons if gallium has no charge. Thus, the problem is really asking us to find a home for 31 electrons. Again, following our 3 simple rules, we place all 31 electrons into our diagram as shown. You are probably thinking that it is going to be very challenging to memorize and reproduce the electron configuration diagram template shown. However, if you have access to a periodic table, you can easily reproduce it. For example, if you simply read the periodic table from left to right, the correct order of orbital filling is obtained. 1s, 2s, 2p, 3s, 3p, 4s, then you go down a level for the 3D, back up to the 4P, 5s, down a level for the 4D, and so on. In addition, the periodic table tells us how many electrons go into each sublevel. For example, the s block is 2 elements across, thus 2 electrons can go into all the s sublevels. The p block is 6 elements across, thus 6 electrons can go in all the p sublevels. The d block is 10 elements across, thus 10 electrons can go in all the d sublevels. And finally, the f block is 14 elements across, which means 14 electrons can go in all the f sublevels. You may notice that when we compare the order of filling we obtained from the periodic table to the electron configuration diagram template, they are the same. Clearly, having access to a periodic table helps us reproduce the electron configuration diagram template. Thus, you should practice drawing this diagram on your own with the aid of a periodic table until you have mastered this skill. As you can tell, the keys to writing electron configurations are to quickly ascertain the number of electrons for an atom or ion from the periodic table, and to be able to quickly reproduce the template for the electron configuration diagram. Remember, you can use the periodic table to help you reproduce it. Then simply follow the 3 basic rules for electron configurations, and you should have no problems determining electron configurations. In the last chapter, it may have seemed difficult representing electron configurations and drawing the full electron configuration diagrams for atoms that possessed many electrons. For example, the 31 electrons that are found in a neutral atom of gallium. Fortunately, there is a much easier way. Abbreviated electron configurations allow us to combine the inert, noble core electrons with the remaining outermost electrons. Therefore, to be able to write the abbreviated electron configuration, we need to first become familiar with noble core electrons. The noble core electrons have the same electron configuration, often termed isoelectronic, as a noble element. To better understand noble core electrons, let's return to the previous gallium example. Recall that gallium's atomic number was 31, which meant we found a home for the 31 electrons of a neutral atom of gallium. The noble elements are the last family on the periodic table. To abbreviate the noble core electrons for gallium, we simply slide back until we reach the first noble element, which is argon. Argon has 18 electrons. Thus, we can abbreviate the first 18 electrons of gallium as the element argon. These 18 electrons begin at the 1s and end at the 3p orbital and are represented by the noble element argon in brackets. Clearly, the abbreviated diagram is much easier to draw than the full electron configuration diagram. In this example, we will first draw the full electron configuration diagram for a neutral atom of potassium, then we will focus on the abbreviated versions. Potassium's atomic number is 19, which means there are 19 electrons for a neutral atom of potassium. Following the Aufbau rule, Pauli exclusion principle, Hünd's rule, the following diagram and electron configuration is quickly obtained for the 19 electrons of potassium. To abbreviate the noble core electrons for potassium, we simply slide back until we reach the first noble element, which is argon with 18 electrons. Thus, we can abbreviate the first 18 electrons of potassium as the element argon. The first 18 electrons of potassium, which begin at the 1s and end at the 3p orbital, are represented by the noble element argon in brackets. The remaining electron in the 4s orbital is the outermost electron, commonly called the valence electron. It is often very important to quickly ascertain the number of valence electrons that an atom possesses. After all, these are the electrons that will be involved in bond making and bond breaking. The noble core electrons will not be involved in bond making and are often called the inert noble core electrons. Thus, let's focus our efforts on the reactive valence electrons. To answer how many valence electrons carbon has, we will first write the abbreviated electron configuration. We see that a neutral atom of carbon has 6 electrons. Thus, the electron configuration for the 6 electrons of carbon is 1s2, 2s2, 2p2. However, we need to write the abbreviated electron configuration to answer this question. Thus, we slide back to the nearest noble, which is helium. Helium will represent the 2 noble core electrons, which leaves 4 valence electrons. It should be noted that we did not have to draw the full or the abbreviated electron configuration diagram to answer this question. We just needed access to a periodic table. For example, if we first slide back to the nearest noble, which is helium, then we can simply count forward to the element in question, and that will equal how many valence electrons that atom possesses 1, 2, 3, 4 valence electrons, which matches our result from drawing the electron configurations. Let's try to answer one more of these questions using only the periodic table for phosphorus. For example, if we first slide back to the nearest noble, which is neon, then we can simply count forward to the element in question, and that will equal how many valence electrons that atom possesses, which is 5 valence electrons. Thus, from the periodic table, we see that there are 10 noble core electrons, which we could represent by placing neon in brackets, and the remaining 5 valence electrons are placed into the 3s and 3p orbitals, which matches the diagrams shown. Having the ability to quickly ascertain the number of valence electrons an atom has is very important in bonding theory, which is thoroughly examined in the next DVD of this series, Introduction to Bonding. The 4 quantum numbers are a direct result from various quantum mechanical equations. These 4 quantum numbers completely describe where an electron can be located. In a more simplified view, one could say that the 4 quantum numbers give rise to the solutions or orbitals that the electrons occupy, or that they give rise to the electron configuration diagram shown, which was covered in Chapter 2. While thorough treatment of this topic is beyond the scope of this DVD, your instructor may ask you to assign the 4 quantum numbers to an electron. Thus, it is worth our efforts to learn about the 4 quantum numbers. The 4 quantum numbers are the principal quantum number, which will tell us the energy level the electron is located, the angular momentum number, which will indicate the shape of the orbital, the magnetic quantum number, which indicates on which axis the orbital is on, and the spin quantum number, which has only 2 possible values, +1/2, which is up, or -1/2, which is down. While this may seem confusing, it is actually very easy to assign the 4 quantum numbers to an electron, as the following examples will demonstrate. After we draw the electron configuration diagram for nitrogen, we see that the last electron occupies a 2p atomic orbital. Thus, the principal quantum number, which represents the energy level, is 2. The second quantum number, the angular momentum number, represents the shape of the orbital, and from the chart, if the electron is in a p orbital, L is equal to 1. The third quantum number, the magnetic quantum number, M, have the designations shown from -L to +L. Thus, this electron in the last 2p orbital has the value of +1. And the last quantum number, which indicates the spin of the electron, is +1/2 because the electron is pointing up. Thus, the 4 quantum numbers are 2, 1, +1, and +1/2. In the next example, we are asked to assign the 4 quantum numbers to the last electron of a chloride anion. From the electron configuration diagram, we see that we need to fully describe the last 3p electron. The electron is in the 3rd energy level, thus n is 3. It occupies a p orbital, thus L is 1. M is +1, and the electron is pointing down, therefore it is -1/2. Thus, the 4 quantum numbers are 3, 1, +1, and -1/2. In the next example, we are asked to assign the 4 quantum numbers to the last electron of an atom of titanium. From the electron configuration diagram, we see that we need to fully describe the second 3d electron. The electron is in the 3rd energy level, thus n is 3. It occupies a d orbital, thus L is 2. M is -1, and the electron is pointing up, therefore it is +1/2. Thus, the 4 quantum numbers are 3, 2, -1, and +1/2. If chemistry is considered to be the central science, then having a basic understanding of the atom and the three fundamental subatomic particles, the proton, the neutron, and the electron, is essential. After all, the student who has the ability to understand the atom can take the next crucial steps to comprehend many different aspects of chemistry.